We looked at an investigation where we investigated growth and decay. So we're going to do a review today so that we really have the material down. So the first example, which of the exponential functions show growth and which show decay? And so remember, they're all in this form y equals, we have a starting value times b to the x, and this is the key right here, the second number that has the exponent. If that number, the absolute value of that is greater than 1, it's growth. If I could write this right here. So if the absolute value of b is greater than 1, it's growth. If the absolute value of b is less than 1, it's going to be decay. So look for that b value. So here, our initial value is actually a 1 right here, and I know that because 3 has the exponent. So here b is 3, so this is growth. 3 is bigger than 1. Here's the initial value 100, and this number 0.25 is less than 1, so this is decay. So there's our b value, 0.25. And this right here, 1 minus 0.10 is 0.9, and that's less than 1, so this is also decay. And here the starting value is 12. So you look at the thing with the exponent. If that number, the absolute value of that, the distance from 0 is greater than 1, it's growth. Otherwise, it's decay. Example 2, a scientist has discovered a new strain of bacteria. The bacteria culture initially contained 1,000 bacteria, and the bacteria are doubling each hour, every hour. Complete the chart for the next 5 hours. Okay, so they're doubling every hour, every half hour. So after the second half hour, this would be 4,000, then 8,000 after the third half hour, and then 16,000, 32,000, 64,000, 128,000, 256,000, and so on. Write a function to illustrate the situation. Okay, so we need a starting value, and that would be at the $1,000, 1,000 bacteria, not dollars, 1,000 bacteria, and it's doubling every half hour. So doubling means our growth rate is 2, and x will represent the number of half hours since we started, hours since the start. So then D says determine how many bacteria present after 24 hours. So how many half hours is that? That would be 48. So this would be y equals 1,000 times 2 to the 48. So it's going to be a pretty big number here. Let's try typing that in. 1,000. It's doubling every half hour for 24 hours. So for 48 half hours, see, it's a very, very big number. So I'm not going to write that down. Okay, the next example is half-life. And so you talk about this a lot in science. The half-life of a radioactive kind of cesium is 13 days. How much will be left after 39 days if you start with 96 grams? So let's write an equation, half-life. So 96, and it cuts in half. And we'll say x is not each or every 13 days. Okay, so if it's 39 days, we have to take 39 divided by 13, which would be 3. So it's been 3 sets of 13 days. So when we plug in, it's going to be 96 times 0.5 to the third power. And then again, we can type that in. 96 times half-life, 0.5. And you can even put this, I put it outside last time, I put it inside. And it was 30 sets of 13 days. And so you can see there's only 12 left. And we started with 96, so that makes sense it's going down by half every 3 days. And if you wanted to, I mean, you could make a table for this too. We could do 96. And then for the first set of 13 days, cut it in half, and then cut it in half again, and then cut it in half again, and we should get 12. Let's try that. So 96 times 0.5, there's the first day, times 0.5, there's the second set of 13 days, times 0.5, and we get 12 again. So there's several ways to do this, but here's the way you set it up with the equation. Let's try the next, there's two left. There's a population of 48,500 bacteria in a colony. The bacteria doubles every 202 hours. What will the population be in 808 hours? Okay, so this is doubling. So let's start with our initial population, 48,500. And it's doubling, so our growth rate is 2. And X stands for every 202 hours. So we have to figure out, all right, 808 divided by 202. How many hours, how many sets of 202 hours is that? And that's 4. So then when we plug in, we have y equals 48,500 times 2 to the 4th power, 4 sets of 202 hours. And let's type that in. Should be, again, a very big number. So times 2 to the power of, there's 4 sets of that. Okay, so it's 776,000 bacteria, which is a lot of bacteria. Okay, last example. In 2000, there were 120 squirrels in Central Park. The population increased by 6% each year for the next 10 years. If the pattern continued, how many squirrels in Central Park this year? All right, lots of information. Let's start with the starting value, 120 squirrels, and it increases by 6% per year. So you take, it's 100% of the year before, plus another 6% to that, and it would be X. And it says if that pattern continued, so it was still 6% each year, and this is 2016, so we're going to say y equals 120 times 1.06. This would be for 16 years. Let's type that in. Let me clear up my calculator. Doc B, clear scratch pad. All right, 120 parentheses 1.06 to the power of 16. So this year there's about 304.8 squirrels. Let's round that to about 305 squirrels this year in Central Park. Okay, so today you're going to practice setting up your exponential growth or decay. Remember starting value, your rate of change. If it's bigger than 1, it will be growth. If it's less than 1, it will be decay.